You usually post maps here. Let's see the first one. Normally it doesn't take this long to come up. I'm not sure why the computers are so slow. Excuse me. All right, let's take a look at the first handout, which is the course information here. This is B here. I actually got a PhD. I got a PhD in inorganic chemistry. I didn't start off as a chemistry major, though. Originally, I started off as a geology major. I was at Santa Barbara City College, which is a community college in Santa Barbara. And I made it all the way up to mineralogy. And with mineralogy, you identify minerals by the shape of the crystals, by the dust they form when you scratch them, etc., color. And at the time I was taking chemistry as well, and with chemistry we were using instruments, more sophisticated instruments. So then I was thinking, wow, the geologists, the technology seems so dated. And so I decided to switch my major to chemistry because it seemed like they used more sophisticated instruments and did more detailed analysis. But it turns out that was naive thinking, because the geologists also use sophisticated instruments as well to analyze their minerals, rock samples. It's just that they were just teaching the traditional techniques of mineral identification. But anyway, I then transferred to UCLA, where I got my bachelor's degree in chemistry, and then went on to UCSB to get my PhD. The Mastering Chemistry, which is this online homework, is not just online homework, but there's tutorials and other stuff. I haven't set it up yet. I'll set it up today, but this is the course code. Mastering Chemistry, like I said, I think yesterday, the course code is valid for 2 years, and you can use it for multiple classes. So you might have it for a different class, maybe biology or whatever else, but you can use it in Chem if you haven't done so. But this is the course ID. It'll be set up later tonight or tomorrow. My office is in room Chem 120, which is just down the hall here. This is my email address and phone number here. You can come. You can reach me either email, phone, or Piazza, and, or come to my office. My office. But it's tricky because my office hours are going to be held either in Chem 120, which is my office, Chem 105, which is the lecture, Chem 108, which is the computer lab, or Chem 162, which is this room. And so during these times, look for me in one of these rooms. I have office hours on Wednesday, after the morning class from 10:55 to 11:55, and then before this class from 12 to 1. On Tuesdays, after lab here, and Thursdays, kind of before lab. If you can't make any of these times, you can schedule an appointment so we can meet that way. All right, what are we doing this semester? We're doing the second half of the general chemistry book, but actually not the whole. We're going to omit some chapters. It's a bit too long. The major topics in the second half would be chemical equilibrium. That's where we're going to focus most of our attention on equilibrium systems, chemical thermodynamics, kinetics, etc. Those are the major topics. The course objective, we want this to be comparable to a CSU or UC course. So we chose our book. We chose our book to be comparable in level. There are different levels of chem books. Depends on. Did everybody have Chem 1A here? Anybody? Okay, so you're familiar with the Petrucci book. Petrucci book is considered a higher level book. Maybe not the highest level book. Like at UCLA right now, I think they're using a book that's a notch harder. What I mean by a notch harder is there's some pretty challenging homework, and they don't spend too much time on the basic stuff. For example, at UCLA, the book that they were using a while back ago had the first 4 chapters of Chem 1A compressed into 1 chapter. And so that would be it. But we're just a notch right below that. And the homework problems are comparable, so it's a challenging book. It being a challenging book, some people look for easier books, just to get the basic concepts. So you might search around and look for that. But Petrucci is a good source. And we'll have exams, etc. This is shown here. This is how you'll be evaluated: exams, quizzes, labs. I have to mention these SLOs. SLOs are student learning outcomes. You've probably seen these in Chem 1A. The Chem 1B, the first SLO I have written here is this chemical reactions. This is writing, chemical reaction, balanced equation. What I expect is a little bit more than this. We'll talk about it when we get there. Here, this safety goggles. Other SLOs include the scientific method, etc. Prereq for this course is Chem 1A, and there's a math prereq too. I forgot to write it down here. I forgot what the math is. Algebra. Required materials is Petrucci. This is the latest edition, the 2017, which is the 11th edition. It's the 11th edition of the hardcover version. There are actually 3 versions of Petrucci in the bookstore. 2 softcover versions. One olive green one, I think blue. Is that Chem 1A? But you want the olive green one. I'm not sure if it's going to say 11th edition. Somebody just mentioned to me it says 4th edition there, so they're confused. But maybe it's the 4th edition of the paperback book, which is the 11th edition of the hardcover book. The hardcover book is a white hardcover, and that's good for both courses, Chem 1A and Chem 1B. So if you have that, okay. The lab manual, this is a bit confusing because the lab manual is not on the shelf in the bookstore. The lab manual, it says go to the textbook office. So as you walk into the bookstore, on the left-hand side, near the back of the bookstore, are some windowed offices, and I think it's the middle office. 117. You have to go there and you have to ask them for this. And what it is it's just like a shrink-wrapped, photocopied lab manual. This. Uh-huh.
What is the significant difference between the 11th edition and the 10th edition for the textbook?
There is. The significant difference is they move some chapters around, but otherwise, no. Not significant. I mean, if you have the 10th edition, that's fine too. Except when we deal with chapter 13 in the 11th edition, that was chapter 18 or 19 in the 10th edition. So everything's moved around. Uh-huh.
Do you highly recommend getting this textbook because it aligns with the homework, or can we use any textbook?
No. You can't use any textbook because the different textbooks will have different levels of problems and different levels of discussion. And so some of the easier textbooks, they leave out the harder or the trickier stuff. And so it makes it easier to read and easier to do, but you're missing out on those concepts, and those concepts are important. What you can always do, because this textbook should be on reserve, we need to get it on reserve in the library. If you have the 10th edition, you could use that. For example, you could buy a 10th edition or a 9th edition, cheap, probably off Amazon or something like that, eBay. And then just go photocopy the homework assignments out of the 11th edition from the bookstore or something like that, if you're worried about it.
I have a question. You said you wanted to get the olive green cover?
Yeah, the olive green cover. Or the white hardcover version. If you look at the olive green one, it should be bundled. I don't think it's going to be bundled with Mastering Chem because the Chem 1A one was bundled, but you can just double check that. All right, the catalyst unfortunately is expensive. This is $20, which is $19.90 something. All right, Also, there was a mistake this semester regarding the lab notebook. The lab notebook is item number 4. The lab notebook was supposed to be a composition notebook, but what they had was they had the formal lab notebook in the bookstore listed for my course. And that was the duplicate pages, spiral bound notebook, and that's a $20 notebook. We don't need that notebook. If you did buy that, you'll need it for Chem 7A and 7B, organic chemistry, but not 1B. For 1B, we're going to use the cheap notebook. The cheap notebook would be the composition notebook that you buy at the office stores. In fact, I was just at Staples. This is not a plug for Staples, but I was there and I saw that the quad-ruled composition notebook, that is with the graph paper in there, with a sewn binding or tape binding, this was only $1 on sale until August 31st. Normal price is $2.20 or something. I think our bookstore probably has it as well, but I was just in there yesterday. I couldn't find it. They used to have it in the engineering section, and it was a little bit bigger composition, a little larger format, but it was still around $2.75, I think. Safety goggles, so the Chem 1A safety goggles should be fine. The scientific calculator, I recommend breaking down. I mean, you might already have a calculator, like a programmable calculator, which is very powerful, but unfortunately the programmable calculators aren't allowed in general chem. You have to use one of the basic calculators. They aren't allowed because they want to get you thinking about standardized tests. If you're planning to go to, let's say, medical school or graduate school or professional school, they're going to make you take standardized tests. On standardized tests, they don't allow programmable calculators. And so you could buy the cheapest scientific calculator. The cheap scientific calculator ranges from a couple of dollars to $10 or something, but I don't recommend those. You could use that as a backup calculator. For this class, I would recommend the like the $15 calculator. The $15 calculator is going to have some more functions to it. One of the functions you're looking for is an equation solver. And so the calculator that I saw, actually this is a calculator I bought. I bought it at Target, and I saw it's at Walmart and Office Depot and a bunch of others. But something comparable, it doesn't have to be this, but this is a pretty popular calculator. Casio FX 115ES, I think it is. This one's allowed on standardized tests, and it does have an equation solver. You'll need the equation solver this semester to save time. And it's worth having backup calculators anyway, so it's worth buying. And so you can find these on Amazon. It's I forgot how much it is. 15, I think. All right, so a scientific calculator, preferably one that has an equation solver, that is okay for like things like the SAT or whatever standardized tests. Item number 7 is fine point permanent marker or Sharpie. Those are handy to have for labeling. These recommended materials are required at UCs now. They require everyone to have a lab coat. It's optional here, but it's worth getting a lab coat, I think. Especially with the chemicals that we deal with. Sometimes there's a little splash. You don't know that a little drop of liquid got on your clothes until you wash it, and then you see there are holes, or there's a hole in your, because something ate through it. So it's nice to have. They aren't that expensive. I bought a lab coat on Amazon for $16. At the bookstore, they have lab coats there for I think $20, $20 to $40. $40. If you get a nice cotton lab coat, those are very nice. The last cotton lab coat I bought was $67. And some schools, UCLA requires cotton because cotton's more fire resistant versus the synthetic materials. So they want something with a little bit of fire resistance to it. Nitrile or latex gloves, you can buy these at the supermarket or wherever. Most places will sell. I prefer nitrile gloves. for two reasons. Nitrile gloves breathe, so you don't sweat as much in them. You know, latex, they tend to sweat in those gloves, and it's hard to work. When your hands are dry, it's a lot easier. And nitrile has better chemical resistance. You know, not all gloves are going to protect you 100% from everything. What happens is, you know, some things will penetrate the gloves. They act, you know, once they become saturated with a certain chemical, let's say latex, you know, latex is exposed to something like acetone. You know, the acetone starts to seep in to the rubber, and eventually, once it's saturated with that, then it offers no protection at all. You have to throw it away. Nitrile is a better chemical barrier, but there are certain chemicals that it doesn't resist very well, and those just seep right in. But for us, these work very well. Nitrile gloves you can use all day, and actually even more, because if you want to reuse them the next day or the next lab, it's possible. I'm not sure what's wrong with our computer. It keeps logging me out periodically. All right, all the assignments are required, you know, attendance, including attendance in lecture and lab, especially lab. You don't want to miss any labs. If you do miss a lab, then try to make up that lab. You know, I have this afternoon lab, but I also have a morning lab. So if you're going to miss it, then try to make it up in the morning. There's usually space of this semester. Sometimes there's no space. For exams, it's a bit more difficult and more complicated. You know, it depends on the circumstances why you missed the test. Because makeup exams are subject to potential penalties, depending on what happened. So don't try not to miss any exams. Quizzes are going to be kind of that random. You know, these are like pop quizzes. We'll just have these spread out periodically through the course. The exams all announce the dates on those, but you can kind of figure it out once we take a look at the syllabus. But the course breakdown is going to go like this. 50% of those will be on these midterm exams and quizzes. 20% of the grade is going to be on the final exam. We have about 1,000 points. Homework is about 10%. Labs are about 20%. This is just a rough point approximation. You know, this will be adjusted as we go along in the course. The quizzes are going to work out to about 1 to 5 points each, so the quizzes aren't going to be worth that many points. Exams between 50 and 65 points, approximately. Homeworks, 10 points per assignment, basically. Labs are 15 points per assignment, except for a couple that are like double, or 3 that are double. Synthesis, titration, rate law, these are more involved. The reports will be more involved. Excuse me, I'm not sure if we'll have 3 double point labs. It might be 2 double point labs. Qualitative is a little more than double because this is a very long sequence of experiments here. Qual or qualitative analysis will be 35 points. The grades are going to be based on the percentage of total points. So 88 and above is an A, 78 is the B cutoff, 65 is the C cutoff here.
Do we need a scan run for the homework, for the exams?
For sure, the final exam you need a Scantron. For the chapter exams, I haven't determined yet, you know, because they're shorter. I'll talk more about the exams in a minute, but the exams are going to be a mix of multiple choice and free response. Depends on how many multiple choice you have. All right. You're probably familiar with this policy here regarding the lab. At UC, the lab and the lecture are separate courses. So I think the lecture course is 3 units, the lab is 1 unit. So if you fail lab, then you just failed 1 unit. okay, but here, if you fail lab, since lab and lecture are combined, you fail 5 units. And it doesn't matter how good your score is in the lecture portion. If you don't pass the lab, you can't pass the course because they're combined. If they were separate, then we could let you pass the lecture, but fail you for lab. Because of the way it's set up here, and our articulation agreement with UC, they won't let us do that. And so if you, this happens every once in a while, I have to fail somebody. They just stop showing up to lab. I don't understand. They'll come to lecture, and I tell them, you know, lab is important. If you fail lab, you're going to fail class. But for some reason, they don't like lab. They do fine on the lecture test, but I have to fail them for the class. But anyway, that's very rare that something like that happens. Note on cheating, when I converted this to PDF, this didn't convert very well. This was supposed to say academic honesty is expected. Different professors have different philosophies on cheating. You know, when I was at UCSB, I was working with some professors who didn't care if somebody cheated. They didn't care if somebody cheated because they figured, you know, pretty soon it's going to catch up. Because as you get to higher and higher level classes, the classes grow smaller and smaller. And so when I was taking upper division classes at UCLA, one of my classes, there were only 9 students. With 9 students, the professor knows, you know, basically, it's easy to tell if you belong in the class or if you don't belong in the class. And if you cheated your way to that class, then obviously you're going to stick out as not belonging in that course. And then there are others that, you know, that are on it, you know. But if I see any kind of suspicion of cheating, you know, I'll definitely be on it to try to prevent that, because I don't want anybody to go on. This is the time and place to get the solid foundation here. All right, if there are any special needs here, make sure you let me know, or you can let the Student or Special Resources Center know. I can help you out with that. If there are any changes, I'll post these on Piazza, or I'll announce it in lecture. This is the definition of chemistry. This definition here is a little different than the chemist definition. You know, a chemist would rewrite this definition as this: the science of the composition, structure, and properties of matter. They wouldn't separate this. They wouldn't say the composition, structure, properties, and reactions, because when a chemist thinks about properties, there are 2 types of properties that they think about. There's the physical properties, and then there's the chemical properties. The chemical properties are the chemical reactions. And so this is not necessary. We can eliminate this because properties should encompass both physical and chemical properties. One of the things that happens, though, is that there's a heavy emphasis on physical properties, but not much emphasis on chemical properties. And so this is why I want to start off this semester talking about chemical properties. So here I had the class intro scheduled for yesterday, but I moved it to here. So I want to show it on the overhead. But we're going to jump into reactions today, continue reactions through tomorrow, and then on Thursday we're going to start chapter 13, which is thermodynamics part 2. And well, we'll talk about this more, but when we think about chemical reactions, like for example, what are the chemical properties? Phosphate. You know, that was a question I had. That is burned into my memory because when I was at UCLA, I had to take one oral examination there. And during the oral exam, they asked me, what are the chemical properties of phosphate? And I was thinking, I'd never really had given it any thought. And so, but I'm a chemist, so I should be able to answer that question. And so I started thinking, well, what does phosphate react with? Does phosphate react with sodium hydroxide? Potassium hydroxide? How would you answer a question like that? And so I was thinking, what do I know about phosphate? So I was kind of at a loss, so I just started, reaching for different things. And one of the things I said, well, it's in laundry detergent, right? So it's a detergent. It's, you can precipitate out calcium phosphate. And that's about it, And the reason I was thinking, why was that the answer? Because there are long moments of silence while I was thinking about this. The long moments of silence, it wasn't really that long, but there's only you standing here, and then there are like 3 people. There are professors there, and so they're waiting for an answer. And so each second, it was like slow motion. Each second was just ticking, and dead silence, dead air. It's like, on the radio when it goes dead, you start to wonder what's going on. Well, this is dead air. I was wondering what. But it wasn't dead for me because I was thinking, and I couldn't put it together. And so I didn't have a good answer for that. I just blurted out some random things it would react with, right? And then I thought, why am I so weak on chemical properties? A physical property is okay. Melting point, boiling point, this and that. But I figured why I was so weak on chemical properties is because of the way it's presented in the book. And so what I'm going to do is I'm going to present it differently than what the book does. So this is not associated with any chapter. It's here. I just made some PowerPoints for this. But actually, you can find the information in the chapters. It's like chapter 5 material, chapter 3 material, chapter 19 or 18 material, etc. And so it's in the book. It's just not organized in a way that makes it easy to use. And so we'll start off with this, and then we'll continue. All right. So what's going to happen is something like this. I'm not sure when we're going to have the test for a reaction. Normally what's going to happen is, let's say we're on chapter 13. We go through chapter 13, and if I stay on schedule, I'm going to finish chapter 13 here on September 6th. The exam will be the next week. The following week, I'll probably put it, if we finish on Wednesday, we'll probably have the exam either on a Tuesday or Thursday. So if we finish Wednesday here, I'll put it on a Thursday here. So we're going to have the test. So not only are we going to do the lab here, we're going to have a test. It's just going to be a test on one chapter, chapter 13, and that's it. Okay, it depends on how people do with this reaction stuff. I might give you more time for that or less time. That is, I might test you on this next week, but let's see how it goes. But for sure, chapter 13, you can expect the exam probably on September 14th. Then we're going to jump to chapter 15. We finish chapter 15 on Monday, September 18th, according to plan here. We should expect the test when? On September 26th. So we'll have like an hour test then. And so that's what, now the homework is going to be collected on the exam days as well. And so the homework for chapter 13 will be due on the day of the test, September 14th, 15th there. If you don't finish it all, just turn in what you have done because you'll get full credit for that. Any homework that's turned in late will lose 50% of its value. And late homework will be accepted all the way to the end of the semester. So if you have some late homework, just turn it in with the final. It should be okay. Quizzes are going to be interspersed here. I'll talk more about quizzes later. All right, obviously we're going to have a problem when we get to the end of the semester. And so we're going to finish chapter 25 on December 11th. Am I going to make you come in on December 19th to take the test? No, nobody's going to come in. So what we're going to do here with chapter 25, and probably with chapter 24, because I don't want to put an exam on chapter 24 the day before the final, right? And so what I'll do with chapter 24, part 2, and chapter 25 is we'll just incorporate those into the final. So I'll put in a few extra questions from 24 and 25 on the final. But that means it's going to get busy near the end of the semester, as it always does, because everything's going to be bumped up. All right, make sure to interrupt if you have any questions, but are we good with this? Uh-huh.
Is every exam only going to be one chapter?
Yes. Every exam will just be one chapter. Except, actually, I should take that back. For example, 24.1 and 24.1 through 24.3 is nomenclature. So I haven't decided if I'm going to make that a test. You know, if this were a test, then I'd test you over here. But we might make this a quiz. Here. It's a little nomenclature quiz. That's the only chapter we split. All the other chapters we cover in full. So we're just going to hit the first part of 24 right at the beginning of the semester. And then the remaining part of chapter 24 will be covered at the end of the semester. We just have to learn how to name it. Well, it's called a coordination compound or a complex ion. Okay, anything else? I have some PowerPoints. Did everybody, was everybody able to access Piazza? Okay. So I put the PowerPoints on there. PowerPoints there. This one's called Chemical Properties Part 1. Chemical Properties Part 1 deals with a certain type of reaction called metathesis. It also gives the kind of intro to it. Here's the definition of chemistry. These first couple of slides are just saying what I just said about the difference between properties and reactions. There's no difference here. So I'm going to skip it. So what chemists do is they study the properties of matter. And so, we want to understand how matter works. And so, for example, one piece of matter would be diamond. Another would be graphite. And so diamond and graphite, they have two totally different sets of properties. Not similar to one another at all, except they're both made out of the same thing. Diamonds and graphite are made out of pure carbon. And so to understand the properties properly, we need to know the composition and we need to know the structure. The structure of diamond is quite a bit different than the structure of graphite. And from those, we try to make correlations between composition, structure, and properties. Better understand this. Here, we always use a mix of descriptive and theory. You know, we can't just start off straight with theory. You know, for example, if you knew the structure, right, could you predict the properties? So if I give you some random structure, can you predict the property? No, what you need to have is you need to have some factual knowledge, you know, some descriptive chemistry memorized. Descriptive chemistry would be something simple like HCl. Let's take pure HCl. If I have pure HCl, is that a gas, liquid, or solid? Pure HCl, gas, liquid, or solid? Well, aqueous is not pure. Aqueous would be a mixture of HCl and water. So that would be a mixture rather than a pure substance. And so it's pure, you know, normally when we think of HCl, it is aqueous, it's hydrochloric acid. Well, this is going to be hydrogen chloride. pure hydrogen chloride? Well, it's a gas. HCl is a gas. And so again, this is going to be a lot easier than trying to figure it out theoretically, using quantum mechanics, using the Schrodinger equation. You just memorize that. If you have that memorized, that serves as like a reference point. It's like moving to a new city. If you move to a new city, you want to memorize some landmarks so you have some kind of geographical reference points that you can fall back on. Well, this is the same thing. When you're learning, chemical properties and chemical reactions, you want some reference points that you can kind of, fall back on. So, for example, if I threw out another compound like HF, is HF a gas, a liquid, or a solid? HF. HF would be hydrogen fluoride. Mixed with water is called hydrofluoric acid. But what do you think HF is? It's a gas. Why? Because, HCl is a gas. I've memorized that. HF should be a gas, right? And so it's just doing this so we have some kind of reference frame that we can better understand chemistry. That's what we're going to be doing. There's a lot of memorization initially because we want to be able to understand, the behavior of certain things based on. So we need to talk. Let me skip this one. This slide is basically saying something like this. Now I know what that beaker was for. Okay, so we have this clear colorless liquid. Is this liquid pure water? Why not? One, it says industrial water, do not drink. So we don't want to drink this, but maybe it's pure.
Maybe it's contaminated.
Maybe it's contaminated. We don't know. What we do is we try to measure some of the properties to see, do those properties match? Things like smell. Probably don't want to taste it, but what else would we do? Boiling point, right? Freezing point. All these things to compare. For water, let's say this stuff boils at 100 degrees C. Would you drink it? It boils at 100 degrees C. Would you drink it? Maybe. Water's supposed to boil at 100. It's contaminated, it might not boil at 100. Maybe it's okay. Would you? Probably not, right? Because there could be some trace contaminants in there. And so sometimes what we do for this is, even though, water is going to have a certain set of chemical and physical properties that we can test it against, sometimes it's too hard, to analyze this for all the contaminants. So maybe the easiest thing to do is just to purify the water. Do you know how we purify water? It's probably a lot easier just to do what? If I want to purify this water, probably the easiest purification technique would be to... Well, filtering is tough because it depends on the filter. A lot of contaminants and impurities will also go through the filter as well. Boil it and distillation, collect the steam that comes off. And so we could distill this and get pure water, and then we can test that against it. And so sometimes it's easier just to purify rather than analyze. Like I said, with physical properties, there's a list of them. Freezing point, boiling point, density. We could measure the density of the water, see if it matches that of pure water, etc. But for chemical properties, this is one of the reasons why I had difficulty trying to answer the question. What are the chemical properties of phosphate. And so when we think about chemical properties, you go back to Chem 4, or actually this is back to Chem 1A. You know, what types of reactions were covered in Chem 1A? You got the combination, the decomposition, the acid base, the single replacement, the double replacement, combustion. If you go back to Chem 4, then the combinations were element plus element, and metal oxide plus water, or this plus that. They had so many subcategories. I think if you look at the Chem 4, if you had Chem 4 here, which is the intro chem, they have like 15 or 20 different categories, didn't they? And so this is not a very good way to categorize chemical reactions, I think. It's not a very good way to categorize chemical reactions because some reactions fall outside the category. For example, this reaction here. This is HCl plus HNO3. You guys know what this is? Should be easy. Hydrochloric acid. This is AQ. When it's AQ, we would call it hydrochloric acid. If it were G for gas, I'd call it hydrogen chloride rather than hydrochloric acid. This is HNO3. HNO3 is called nitric acid and gold. And so how should I categorize this reaction? Should I categorize this as the hydrochloric acid, nitric acid, gold reaction? And then start memorizing all the individual reactions and all the individual combinations that take place? No. What I want to do is I want to categorize them into simpler categories, types of reactions. Now, this is a very famous reaction, though. Do you know what this reaction is called? It has a name. Actually, this has a name. The mixture of hydrochloric acid and nitric acid is called aqua regia. Aqua regia is like golden water. It's golden water because aqua regia dissolves gold. Now, how does aqua regia dissolve gold? Well, aqua regia dissolves gold because this is a very special reaction. You just memorize it? No, it's because this is a combination of redox and acid-base chemistry that's happening. So it's two types of reactions. And so this one falls outside the category, but we need a different categorization system so that this falls inside the categories. Sometimes the categories are confusing because both of these look like combination. You're taking A plus B yields C, A plus B yields C. It's kind of like a combination, maybe a little bit more complicated, but these two reactions are totally different. Even though you're taking two things and forming one, they're totally different. And so you wouldn't categorize these the same. This is why Chem 4 does this. Element plus element. Metal oxide plus non-metal oxide. Metal oxide plus water. Non-metal oxide plus water. Do you remember all those categories? So many. Well, how many categories should we have? When you think about all the reactions that take place, just in your body or around you here, there's so many. And so aren't there like an infinite number of chemical reactions? Therefore, an infinite number of chemical properties? No, I would propose that there are three basic types of reactions. These are the three basic types of reactions. Metathesis. Metathesis is like double replacement, but I don't call it double replacement because double replacement, you have to fit a form. Metathesis, you don't have to fit any form. Acid base and redox or oxidation reduction. These are the three basic types. All the reactions that I've shown can be categorized into one or multiple categories here. And the three basic types are distinguished by what I call the driving force for a reaction. The driving force for reaction, what drives the reaction? In nature, as I said, I think yesterday, nature tends to minimize energy. High energy things are unstable, like this, right? Lower energy things are more stable, like this. And so driving force in these reactions is going from less stable reactants to more stable products. Like that. We can do an example of this. Let's take a look at an oxidation reduction reaction. We can do this here. I can take some methane. I got methane here and oxygen in this room. And so if I mix methane and oxygen, oxygen's a gas, methane's a gas. Clear, colorless gases, both of them. Is that a stable mixture or an unstable mixture? Methane and oxygen. So if I continue filling this room up with methane, I'm creating a dangerous situation, right? It's unstable mixture. This is an unstable combination. And so this is like this. This is high energy, unstable. What's the temperature? Is it unstable because it's high temperature? Is it a high temperature? Is this mixture a high temperature mixture? Is it hot? Is it going to release a lot of heat? Is it hot? Is this mixture hot or? No, this mixture is at room temperature. It's a hot. No, it's not a hot mixture. It's a room temperature mixture. Is this mixture going to release a lot of heat? Let's see. When it reacts. When the mixture reacts, will it release a lot of heat? Yeah, but is it a hot mixture? No. It's a room temperature mixture, but it releases a lot of heat. What is room temperature? Well, today room temperature is kind of on the cool side, 20 or something. But chemists have a room temperature that they have in mind. If somebody uses randomly says this is a room temperature mixture, what temperature are they referring to? Are they referring to the actual room temperature or the standard room temperature that people say? It's not really. This is the accepted room temperature. What is the accepted room temperature? 25 degrees C. So we'll just say it's close. So it's at 25 degrees C. When I combust this, it's going to form a more stable product mixture. The more stable product mixture will be CO2 and H2O. Let's balance this. Initially, the CO2 and the H2O will be hot as the flame. But eventually, what's going to happen to the CO2 and H2O? It's going to cool back down to room temperature. Is it going to stay hot forever? No, it's not going to stay hot forever. It's going to cool back down to 25 degrees C, and so this is why H2O at 25 degrees C is a liquid. It's not a gas. And so I write H2O liquid. If I want to make this H2O gas, then I need a temperature greater than this. I need a temperature of 100 degrees C, but is this room 100 degrees C? No, this room's a room temperature. So it's going to cool back down to room temperature. All right, you need to review, because we're doing thermodynamics soon, but we're going to need to review some thermodynamics too to understand these chemical reactions. But this is a redox. For redox, what makes this unstable? What makes this stable? And so these are the reference points that we want to start memorizing. And one of the things you can do is this. You can analyze this. Let's analyze methane. What about methane makes it particularly unstable? Obviously, it's unstable because if we fill this room up with methane, it's kind of dangerous. And so what about methane that makes it unstable? Eric, you have it? Yeah, good. We would look at the oxidation state. The oxidation state, but it's not just the oxidation state. Oxidation state's a number. It's just like a tool. The situation with the oxidation state is you have to learn how to use them. And so, what is the oxidation state here? Hydrogen is +1. Carbon is -4. This is from chapter 3. A lot of people can calculate oxidation states. It's not difficult. You know, go back to chapter 3, you follow the rules. The problem is nobody knows what they mean. They can calculate it, but they can't tell you anything about them. So carbon at -4, what does that mean to you? Well, in terms of redox, we have to look in terms of redox chemistry, because redox chemistry, we have oxidizers. Now, oxidizers want to do what? They want to take electrons. And we have reducers. Reducers want, or they don't want to, but they give up the electrons. So we have oxidizers, we have reducers. And so something wants to take electrons, we call that electron poor. If it's electron poor, it really wants electrons. If it can give up electrons, we call it electron rich. And so in terms of redox properties, we think conceptually in terms of electron rich and electron poor. Is methane electron rich or is methane electron poor? What would you say? Well, here you have to know something about carbon. If you look at carbon, carbon's kind of in the middle. If carbon gains 4 electrons, it would be isoelectronic with neon, it'd have an octet. If it loses 4 electrons, then it'd be isoelectronic with helium, it'd have a duet. And so carbon can either gain 4 or lose 4. That's typically what we see, or somewhere in between. And so in this case, carbon's gained 4. Hey, does CH5 exist? Can carbon gain 5 electrons? So I'm going to go for 5. If I want CH5, then I could have carbon gain 5 electrons. The carbon would be -5. Is that going to work? No. No. This is with the max. These are the limits. What we do, we always want to know the limits, you know, what the extremes are, and then everything else is going to be in between the two extremes. Let me see how it goes. And this would be for carbon here. Yeah, obviously this doesn't exist because the 5th electron would go where? It would go in the next shell. It's unbearable. And so this is as good as electron rich as carbon gets. Now hydrogen, well, hydrogen's poor, isn't it? Because it's lost an electron, right? But is it really poor? Think about water here. Water, what's the oxidation state on hydrogen and water? It's +1. Is water poor? Water really wants electrons because the hydrogen is +1, it's going to take electrons. Water is going to be what we call an oxidizer because oxidizers take electrons. So is water a powerful oxidizer? No. Is water water is extremely weak. So that tells me that H with a +1 is no problem. So I kind of ignore it because it's not going to be that significant. And then we look at oxygen. Well, oxygen must be very happy as is because oxygen's 0, right? Elements in elemental form are 0. And so this means that it's neither lost nor gained electrons, so we're good. Is that good? Is oxygen at 0 happy or unhappy? Unhappy, because it would rather be, what would oxygen rather be? -2. Is water stable or unstable? Water is very stable. And so that must mean oxygen at -2 is stable. And so this is what I mean by having some kind of reference points. These things you have to memorize. Otherwise you can't use the numbers, right? If you don't memorize some kind of meaning to the values. And you want to usually memorize the extremes. This way, if you're given something, then you can actually do, for example, let me ask you, hey, I ran out of methane, but I do have some vinegar. Will vinegar combust? Acetic acid? Can you burn acetic acid? Does acetic acid burn? Well, let's think about that. Well, let's think about what else. Acetic acid is, what is it? C2H3O2, good. That's acetic acid. Does acetic acid burn? Well, methane burns. Methane is what we call a fuel. Oxygen is the oxidizer. Fuels have electrons to give out. Does acetic acid burn? Well, when we analyze this for redox properties, the first thing we do, like Eric said, is look at the oxidation state. So that's what we do. Hydrogen goes first, +1. Oxygen's next at -2. That leaves carbon at 0. Is carbon 0 capable of losing electrons? Well, you think it's happy, right? But this is the other, what we try to do is we try to memorize descriptive chemistry. One of the descriptive chemistry things we might memorize is something like this. Does carbon monoxide burn? Can you burn carbon monoxide? Yes. Carbon monoxide is what we call incomplete combustion. We can burn this all the way to CO2. And that is, carbon is +2 here. Oxygen is -2. And so if we combust this, we can combust it all the way to +4 here, -2, just by burning this some more. In other words, oxidizing. Hey, you know what? I'm going to take the CO2 and I'm going to really burn it hard. I'm going to burn it so hard, I'm going to create carbon trioxide. And so I want to burn my CO2 to carbon trioxide. That is, I don't want it to stop. I'm just going to keep burning, burning, and burning it until it burns to carbon trioxide. Am I going to be successful? I mean, really intense combustion. Will I be successful? What do you think? Keep burning it. In fact, you know what? I don't want to stop at carbon trioxide. I'm going to go to carbon. What would you call that? Carbon tetroxide, right? Or maybe even carbon pentoxide. If I really burn it. If you really burn it, can you get carbon trioxide, carbon tetroxide? When we do combustion, sometimes we don't burn it enough. If I don't burn it enough, I might end up with this. Do you know what this is called? It's black stuff. You might have seen it in Chem 4, in chimneys and smoke, particulate matter. It's called soot. Soot, it looks like diamond, but this is not diamond. It would be great if you can burn stuff and form diamond. Or it's not graphite. Graphite's really hard to burn. This is amorphous carbon. It's another structure of carbon. And soot, can you burn soot? Usually soot occurs as black carbon deposits on stuff. So some people try to get carbon decarbonizers, and some people just scrape it off with a steel brush or scrape it off. But some people will burn it. Will get a torch and just burn it. It takes a long time to burn it because it doesn't combust very easily. But they can burn it. Eventually they can burn it to carbon monoxide, they can burn it to carbon dioxide. Can they burn it to carbon trioxide? Yes or no? Why not? Why can't I form carbon trioxide? Why can't I form carbon trioxide? This is why, this is why you guys should review the stuff we cover in class. Usually I try to review it fresh. When I was a student, I tried to go back through all my notes and then write down as much stuff as I could remember. So I would have it complete, and then I'd start. I start studying for the final. Actually, when I was a student, I'd start studying for the final the first day of class. Because I got into a system where, at least 3 or 4 times a week, I would review all my notes from day 1 to the present day. And so everything was fresh in my mind. But no, the reason is because of this. If we lose 4 electrons, we've lost all its valence electrons. If we go to this is -2. That means carbon is plus 6. What's special about carbon in the plus 6? Carbon in the plus 6 means it's lost every single one of its electrons. All 4 valence electrons plus its 2 core electrons. Is that going to happen? No. And in fact, this is ridiculous because unless this were peroxide, but let's say it's not a peroxide, it's an oxide. And this is minus 2, that means this is plus 8. Does carbon even have 8 electrons? No. These are just completely out. And so, so this would be the max. And we see this. We can't form carbon trioxide, but we can form this. What's this called? This is carbonate, and carbonate has an oxidation state on carbon of plus 4. So plus 4 is the max, right? And so let me ask you the question again. Can we burn acetic acid? Will acetic acid burn? Well, how many people say yes, acetic acid burn? 1? Okay. 2? How many people say no? No. Yeah, a lot of people will memorize inorganics don't burn, organics burn. And acetic acid is considered, well, what is it considered? But it turns out acetic acid does burn. You can burn this. In fact, unfortunately, maybe it's fortunate, maybe it's unfortunate. Like if you put oil and vinegar on a salad, you're definitely going to get calories from the oil. Will you get calories from the vinegar? Is the vinegar 0 calories? No, it's not, because what's going to happen is it's going to burn in your body. So if you can consume oil and vinegar, you're going to burn the vinegar in your metabolism, right? And you're going to burn it all the way to CO2, which you are going to exhale, and you're going to get the energy from that. Right? And so, yes, we can burn it, but only the CO2. And it doesn't happen, and there's no flame in your body. It happens by a different step, but from thermodynamics we know something. We know about state functions. What are state functions? This is from chapter 7. I'm sorry, can you? Okay, I didn't quite.
No, I'm trying.
Okay. A state function? Somebody tell me what a state function is. Okay, yeah, you'll definitely have to review chapter 7. A state function, Eric, you got a state function?
I'm a little rusty on it.
Okay, that's okay. That's summertime. But the state function only depends on the final and the initial. It doesn't depend on how you get it there. So whether you burn this in your body or you burn it in a flame, it doesn't matter. You're going to get the same number of calories, because it doesn't matter how it gets there. And that's what we deal with here. We're dealing with state functions. And talking about these, we just care about the final and the initial. How did it get there? You know? Well, how it got there is something a little different, because you know, when I look at this reaction, I'm only seeing the initial and the final state, right? And so let's do this again. Be quick. No, I guess I didn't. Difficulty. All right. Should do. State functions just deal again with the final initial. And it really doesn't matter how it gets there. But in this case, we can burn it. I'm burning methane here, but we could burn the acetic acid as well. But tell me, what is the blue stuff there? I know that blue stuff must be water, right? Because water is blue. Is water blue? The oceans are blue. Or maybe that must be oxygen because the sky is blue. Right? Sky is blue, therefore because we have 4 choices. It could be methane. Methane's not blue. Is oxygen blue? No, oxygen's not blue because otherwise we'd see it in the lab here, right? Air is a mixture of oxygen and nitrogen. CO2 blue? Water blue? No. And so when we do this, when we look at the energetics of this, we're just looking at the final initial. This is state function. We aren't worrying about what's happening in between. And there's a lot of stuff happening in between. The blue is actually from some of the stuff happening in between on its way to completing the reaction. The flame is what we call the 4th state of matter. Well, this is the last one. But anyway, going back to this here, this is important in terms of energetics. Now, when we think about energetics, heat is evolved. So normally when people think of heat, they think in terms of, delta H. Right? Do you guys remember this? Delta H? What is delta H? Enthalpy. What is enthalpy? What exactly is enthalpy? I don't understand enthalpy. What is it? Give me like a simple way of understanding enthalpy and what it is. It's the whole topic of chapter 7 was enthalpy. I think enthalpy was the key. Wasn't it the key thing out of chapter 7? Was it the key concept out of chapter 7? Pretty much. So what is it? The key concept out of chapter 7 is enthalpy, which is the internal. No, it's not the internal energy because we gave the internal energy a different symbol. Do you know what the symbol we gave for internal energy is? Or Petrucci gives? Delta U. Delta U is internal energy. Right? Delta H is not the internal energy. Delta U is the internal energy. Well, it doesn't matter. What is internal energy? What exactly is the internal energy? And what's the difference between internal energy and enthalpy? It's, the calculations are easy. Ask me to do a calculation. The calculation delta H. Delta H is the sum of the delta H of the formation of the products minus the sum of the delta H is the formation of the reactants. I just look up the numbers, plug in the numbers into my equation, I'm done. The calculation's easy, right? The problem is people don't know what the number means. What does that number mean exactly? And what does this little symbol mean? This little symbol here. Standard. I'm sorry, what was that?
Conditions.
Standard conditions. That's exactly what it means. What are the standard conditions?
Room temperature.
Room temperature is not a standard condition.
Pressure.
There's something called STP. It's not STP. STP would be 0 degrees C. It's not room temperature. Temperature is not a condition. It's not a standard condition because most of the reactions we'll do it at room temperature. But there are some reactions we want to do at elevated temperature, some we want to do at lower temperature. So not all temperatures are the same. We don't do that much at STP. Let me take a little side. Actually, we'll stop in a little bit. A little side note here. STP was significant for me because I remember STP very well. I learned about STP in high school. And I think there is where I memorized 22.4. Did you ever memorize 22.4? Yeah? 22.4, I memorized that. 22.4 liters per mole of gas at STP. I had that memorized, and I've been trying to forget it ever since, but it's impossible to forget. You know, I don't know. There's some things I want to remember, I can't remember, and this number I cannot forget. I'd like to forget it so I can free up some more neurons from memory, but I can't. And the unfortunate thing is, do you know how many times I've used it since I've memorized it? 0. The only time I had to use it was for a test. You know, what is STP? What's the volume of gas at STP? Oh, 22.4. That was the only time I used it. It was a complete waste of memory space. I mean, what would have been much more useful is this. What is the volume of 1 mole of gas at 25 degrees C, or room temperature? You know, because I know 1 mole of methane would occupy 22.4 liters at 0 degrees C in 1 atmosphere. But what would 1 mole of methane, what volume would 1 mole of methane occupy at 1 atmosphere in 25 degrees C? That would be a much more useful number. Because, do you guys remember work? It would be much more useful because I know that number. I memorized it. I memorized it as 24.45 liters. And so if I have 1 mole of methane, 25 degrees C, 1 atmosphere, that's 24.45 liters. 2 moles of oxygen at 25 degrees C, 1 atmosphere would be double that, right? And so I could do calculations quickly because this would be about 25 liters. This would be about 50 liters. So altogether I have 75 liters here. And then over here, 1 mole of CO2 would be 25 liters. And this is 2 moles of liquid water. 2 moles of liquid water, each mole is 18 grams. This would be 36 grams of water. 36 grams of water is 36 milliliters. 36 milliliters is 0.036 liters. So this would be about 25.04 liters. And so we're going from 75 liters to 25 liters. Is work done? This is why you have to remember chapter 7 too. Was work done? If we go from 75 liters, initial volume, to 25 liters, final volume, was work done? Yes. Who did the work? Did the system do the work or did the surroundings do the work? The surroundings did the work. So if this were an internal energy diagram, it would look like this. It looked like the surroundings did work on the system, so the energy of the system goes up, and then the rest is heat. Because of this, delta U is equal to Q plus W. We give this equation a name. Do you know the name of this equation? The name of that equation is the first law of thermodynamics. This is the first law of thermodynamics. And this would be the internal energy. What was the internal energy again? It's the kinetic energy plus the kinetic energy plus potential energy. In other words, it's called the total energy. And so U initial would be the potential energy initial plus the kinetic energy initial. U final would be the potential energy final minus the kinetic energy final. And we do this, when we have a chemical reaction, we always do this. We always start the reaction at a given temperature. It doesn't have to be 25, but what we'll always do is we'll always end the reaction at the same temperature. We always end the reaction at the same temperature to keep something constant. Well, one thing that's going to be constant is the temperature is going to be constant, right? We start at 25, we end at 25. What else is going to be the same between the initial and the final? If the temperature is the same, then we know that temperature is a measure of what? This will be from the gases chapter. The gases chapter was chapter 6. So you should review the gases chapter 2. If the temperature is the same, then the energy is the same. Which energy? The kinetic energy is the same. And so what we're doing here is we're doing this. We don't want any change in kinetic energy, because when we have a change in kinetic energy, the temperature changes. When temperature changes, Q is equal to the amount times C times delta T. That's a change in kinetic energy that's going to result in this. When we have a change in potential energy, it's a little different. Q is equal to the amount times delta U, or the amount times delta H, depending on what conditions we do it. Whether we do it under delta U conditions or delta H conditions, right? What's the difference between delta U conditions and delta H conditions? When do we use delta U, when do we use delta H?
Delta U is for when there's work.
Um,
Or you.
Delta H is work too. There could be work in both. This is it. I told you I transferred. I'm going to spend just another minute. I told you I transferred to UCLA. The first class I took at UCLA is thermodynamics. Thermodynamics is this stuff. I could do all the delta H calculations, no problem. I could plug in the numbers. The problem that I had with thermodynamics is I didn't know what anything meant. And so when I was in thermodynamics, I bombed that class. The first exam, I think I got like a D. I couldn't believe it. I was prepared. I couldn't believe it because I was prepared. When I transferred there, they said, you're going to watch your GPA drop by 1 grade, when I went to the orientation. And so I said, no, I'm not. I'm going to work so hard, my GPA is going to stay up, right? I don't want it to drop at all. And so when I got the results of that first test in thermo, it just blew me away. I just couldn't believe it. And the thing I couldn't believe was I studied so hard for that test and still blew it. Because all I did was study. I didn't do anything else because, I wanted to do good. And so I thought, I don't have any more minutes. And I wasn't sleeping much anyway. I didn't have any more minutes to study. Although I was working at the time. I was working at the cafeteria. And one thing that did impact was before tests and before the final, a bunch of people quit. So they increased the number of shifts. But still, I didn't do anything else. I just had time to study. That was it. But it turns out the way I was studying is wrong. So I totally changed the way I studied and then corrected that. I couldn't study the same way I was studying at Santa Barbara City because it just didn't work in UCLA. And so I changed and I changed the way I thought about these things. I didn't think about these things as being these calculations. I thought about these things. Each of these you have to have it defined. For example, if you use delta U when the conditions are for delta H, then you just screwed it. You got the total wrong answer. There's 0 points. And so that's. Well, how do you know that? There's no alarm that goes off that says you're using the wrong equation. You're supposed to have this all memorized. Well, this is good now because you're just still at the base level. We're still at the general chemistry level, so now you have a chance to learn all the definitions and learn the definitions well, so that if you do take thermodynamics, and you'd be surprised at how many people have to take thermodynamics. They have thermodynamics for biologists, because they want to figure out how many calories you burn, right? They have thermodynamics for engineers. They have thermodynamics for chemists. They have thermodynamics for physicists. And thermodynamics is generally known as a challenging course. If you go on the discussion boards, I was looking at the discussion board one day. I don't know why I ran across it, but it was like a Harvard discussion board. What's harder, thermodynamics or organic chemistry? And so they're debating both sides of that. But it's tough. It's tough not because the equations are so tough. It's tough because you got to memorize all the definitions and all the connections and when it's okay to use, when it's not okay to use, and this kind of stuff. If I didn't change the temperature here, then I have to add another factor into my equations when I do the calculations for this. If I had the temperature up here or down here, then there's another element where it's not so, so simple. And so those types of things are the things you want to start reviewing from Chapter 7. Anyway, I will talk. So we have this. Now, standard conditions, let me just finish with this and then we'll go on a break. What are the standard conditions? It's not temperature. Temperature is not a standard condition. this is a thermodynamic standard conditions. Thermodynamic standard condition would consist of one, pressure. What is the pressure? The pressure is going to equal 1 atmosphere or 1 bar. This is going to be a standard pressure. Okay, and 2, melt volume. If we had a solution, the solution would be at 1 molar. Those are the standard. The pressure is going to be at 1 atmosphere or 1 bar, and the concentrations are going to be at 1 molar. So this means we have to review chapter 6, because chapter 6 is this. Let's just take a simple mixture. If I have air is a mixture of nitrogen and oxygen. Air consists of let's say about 80% nitrogen, 20% oxygen. And so if I have 1.0 liters of air at 1 atmosphere, how many liters of nitrogen do I have? Or, okay, how about this? If I have 1 atmosphere of air, how many atmospheres of nitrogen do I have? You guys remember Dalton's law? P total is 1 atmosphere. What is the partial pressure of nitrogen? It's 80%. That means 80% of the collisions against the wall will be nitrogen. And these collisions generate the pressure. 20% of the collisions will be oxygen. And so if I take all the collisions taken as a sum total, I have 1 atmosphere. If I just ignore the blue collisions, what would the pressure be?
Of
0.8?
1 atmosphere.
Yeah, it would be 0.8 atmospheres. And so, according to Dalton's law, I'm going to have 0.8 atmospheres of nitrogen. And I'm going to have 0.2 atmospheres of oxygen. So is this under standard conditions? Standard condition says I should have 1 atmosphere. So if I take the oxygen from this air and put it in here, is that under standard conditions or non-standard conditions? Non-standard conditions, because it should be 1 atmosphere. But it's actually under standard conditions. It's actually under standard conditions because there are 2 ways of looking at a gas mixture. And these are the 2 ways. Let me just finish with this. And then go on break. The 2 ways of looking at a gas mixture are this. Dalton's law is going to say if I have 0.8 atmospheres of nitrogen, how many liters of nitrogen do I have? So I just want to look at the nitrogen. In 1 liter of air, I have nitrogen. It's going to be 0.8 atmospheres of nitrogen, and the volume of the nitrogen will be 0.8 liters or 1 liter. No? How many? 0.8 liters of nitrogen? Actually, 0.8 liters of nitrogen is wrong because of the way I'm visualizing this. What I'm going to do is I'm going to take a mixture and I'm going to separate it into 2 containers. If I have 1.0 liters of air, I'm going to take the oxygen out of here. If I take the oxygen out of here, then I'm going to have 20% fewer collisions. And that's going to give me my 0.8 atmospheres. And so it's going to be 0.8 atmospheres of 1.0 liters of nitrogen. Okay, in another box, I'm going to put the oxygen. The oxygen now, without the nitrogen here, the oxygen's in the same size box, but without the nitrogen, there's going to be 80% fewer collisions. And so the oxygen here is going to be 0.2 atmospheres at 1.0 liters of oxygen. This is Dalton's law. Dalton's law says that the partial pressures add up. So 0.8 atmospheres plus 0.2 atmospheres equals 1 atmosphere. But the volumes are constant. And so here, 1 liter plus 1 liter gives me 1 liter plus 1 liter gives me 1 liter. 1 liter plus 1 liter gives me 1 liter. Volume is constant. We're going to put it in the same container. Does that make sense? We could do this exact same mixture, but we're going to look at it in terms of Avogadros. And the reason I review this is because our book emphasizes Daltons, and so a lot of people forget about Avogadros. In thermodynamics, in chapter 7, all our mixtures were Avogadros mixtures, not Dalton's mixtures. And so this is the way we think about it. The way we think about an Avogadros mixture is this. If I have 1 liter of air, I'm going to have, rather than 1 liter of nitrogen, I'm going to have 0.8 liters of nitrogen. But the 0.8 liters, I'm going to cut the volume by 20%. But I removed the 20% that was oxygen of those collisions, and so I'll end up with 1.0 atmospheres. And then I'm going to have 0.2 liters of oxygen. And the 0.2 liters, well, I'm going to take away 80% of the volume, so the number of collisions will stay the same as before, and I'm going to end up with 1.0 atmospheres of oxygen. This is of nitrogen, this is of oxygen here. And so in an Avogadros, it works like this. 0.8 liters of nitrogen plus 0.2 liters of oxygen is going to give me 1 liter of air. And then 1 atmosphere plus 1 atmosphere gives me 1 atmosphere. That's Avogadros. Dalton's is 0.8. In Dalton's, the partial pressures are additive. In Avogadros, the volumes are additive. In thermo, we always use Avogadros. For example, if we use Dalton's, we'd have to do this. If we use Dalton's, I have 1 atmosphere of methane. I better put in 2 atmospheres of oxygen, because 1 atmosphere of methane needs 2 atmospheres of oxygen. 1 atmosphere plus 2 atmospheres gives me 3 atmospheres total. But I want to think in terms of Avogadros. In terms of Avogadros, it would be 1 liter plus how many liters? 2 liters. And this would be 1 liter of methane at 1 atmosphere plus 2 liters of oxygen at 1 atmosphere. And this will give me a total volume of 3 liters. And that pressure will be 1 atmosphere. And so when we're doing this, although, in chapter 7 is when we first started discussing this. When we do this, we have to think in terms of this. We cannot think in terms of this. It doesn't work. And so we don't think in terms of pressure, we think in terms of volume, additive volumes. And so this could be 10 liters, this would be 20 liters. It's double the volume. That's Avogadro. So I want you to review that too. That's in chapter 6 as well. We're going to need that for thermal. All right, let's stop here. We're going to take a break. We'll take a break for 15 minutes and start again. Say at 3:45.